Okay, cool. Lovely to see you all this morning. Um, yeah, the thing to stress, so this lecture is technically titled uh, the second part of FOL natural deduction. That's really just in case it was necessary to go back over the material. But in terms of the natural deduction stuff, as with so many of these things, it's not really helpful to have a second lecture so much as just more time in the tutorials to work through problem sets. So what I've decided to do is this lecture is on entirely supplementary material. It's kind of just fun stuff or interesting stuff to think about rather than material that I'm going to examine you on. So in particular, what I want to talk about is first a notion of duality. So this is something we've come across already, and it's a relationship that holds between connectives. And talking about duality will then let us get to this notion of expressive adequacy. And really, when I say expressive adequacy, it's how many connectives do we actually need? If we wanted to recover a system that works exactly like TFL, how many connectives do we actually have to have? So we'll go through those, and then we'll pivot in basically the last real section and talk about what we can call non-classical logics. So it'll be easier to talk about when we get there, but these are logics that give up on some of the fundamental assumptions we had at the very beginning. In particular, the ideas that there are no gaps, that there are no gluts, and that there's only two truth values. And you get some fun stuff when you give up some or all of these. So I'll just kind of mention them. The slides have links to Stanford Encyclopedia articles if you're interested to find out more about them. But it's just a kind of like, hey, here's some more cool Pokemon. Go look at them. Rather than anything deep and dark. So that's the plan. Let's start by talking about duality. So the place to start here is to note the De Morgan laws. Right? Remember, we have these as additional rules in our natural deduction systems, and they let us manipulate sentences of certain structures. In particular, we have a mapping between conjunction and certain forms of disjunction. So if you have a conjunction, it's going to be logically equivalent to a disjunction with two negations. Similarly, the disjunction can be mapped back to this structure. Now, the neat thing is that this goes both ways. Whenever you have a conjunction, you can turn it into something with just negations and disjunctions. Whenever you have a disjunction, you can turn it into something with just conjunction and negation. Duality is the generalized version of this systematic link between disjunction and conjunction. Now, these are the only ones, and the way that we've formulated it, where we have a very clear mapping, but we can talk about duality generally. So we can just introduce any n-place connective. Right? We can talk about the dual of that by just, again, having this kind of mapping. So the dual of our randomly introduced, we haven't defined, but we're just having it as like a sexy swash font, basically, two-place connective is going to be this kind of structure. And note, if we go back a slide, you can see it, right? You have conjunction, so over here you have the negation, and then you distribute all the negations across using disjunction. Same thing the other way. So in here, we're just using some kind of general two-place or n-place connective. Every atom's going to get negation. We put a negation in front. That's going to map it to its dual. Note that the dual of a dual should always take you back to the original. It's actually kind of hard to show this, but I can give you a quick and dirty version of the proof, right? It goes like this. So we start off with our definition, right? Remember that this is the dual, and this is the initial n-place operator we want to do. Well, we can do this thing of contraposition, where if we add negations on the left, we can also add negations on the right, on the n side. We can then, right, just simplify out with some versions of double negation. Then by double negation elimination, we can reduce down. Finally, we can introduce the dual of the dual, which again is going to be defined using the exact same structuring. And the really cool thing then is because this is effectively entailment both directions, we can then use transitivity of entailment to give us dual of dual is identical to original. Again, don't stress too much if that was quick, because it is quick. I'm just sketching it. If you're interested in the proof for this, Tim, my buddy, goes through this a little bit more detail in the MetaLogic textbook that's also available on the Canvas page. But the cool thing then is, right, when you think about the relationship between, say, disjunction and conjunction, whenever you introduce the dual, well, you're really just coming right back around. So the dual of a dual is always going to be your original operation. What this idea of duality lets us do is introduce the concept of what we can call normal forms, or normal form theorems. Normal form theorems are basically ways for us to derive tautologically equivalent sentences in particular kinds of structures. So what we can talk about is a disjunctive normal form. We're going to have two, just for sake of kind of introducing the idea. Disjunctive normal form is a sentence with the following kind of broad structure. Right? It's only got three kinds of connectives: negation, conjunction, and disjunction. It's got them in a very particular distribution. Negation always has minimal scope. So that is, if there are any negations, it only applies to atoms. Right? Importantly, conjunctions always are inside the scope of any disjunction. So it's basically guaranteeing you've got disjunctions at the highest level, then conjunctions, and then possibly negations. The cool thing is that every sentence can be turned into a disjunctive normal form. No matter what truth functional operators it has, we can turn it into one that only has those three connectives in that particular order. So here's how we can do it. Let's just take any random TFL sentence. Right? What we can do is build a truth table for it. Right? Again, we've just quickly done that. Now, once we have that truth table, you can extract all of the cases where the sentence is true. So what you get then is a distribution of atoms, or if it's ones where the atom is false, you add the negation. So in this case, right, it's true on line 1, so we get A, B, C. It's true on line, 4, so we get, because A is true, we get A, negation B, negation C. Note what we're doing is effectively, to go back a slide, building these. And then what we're going to do, once we have all of the cases where the sentence is true, we then just join them. So this sentence will be tautologically equivalent to the disjunction of all of those. And what this does is it gives you a way to take any sentence and turn it into one that has that disjunctive normal form structure. That is, disjunctions at the highest level, conjunctions the next level down, and then negations with minimal scope. It's just a way to kind of manipulate the structure of sentences. So it's kind of cool. And note, I picked a random TFL sentence, but we'd be able to do it with any TFL sentence at all. This same basic process. You make the table, you extract the instances. If the atom is true, it goes into the conjunction. If the atom is false, the negation goes in. You get the conjunctions for each bit, you disjoin them, boom. You've got your disjunctive normal form version of a sentence. We can also do this with conjunctive normal form. Right? Because, of course, it's going to happen, right? If conjunction and disjunction are duals, then we can use the story about duality to just make a disjunctive normal form, apply the duality rules, and get it into conjunctive normal form. More generally, C and F is just going to be the same three. You've just flipped the scope of disjunction and conjunction. Negation has minimal scope. Every occurrence of conjunction is inside the scope of disjunction. So bang, bang. Interesting thing to note here is negation. And I didn't really talk about this earlier because showing it's fun. But negation is the only TFL connective that is its own dual. Which makes sense, right? If you have negation as a flipper, no matter what you feed in, if you just stick another negation in front of it, you are going to get the dual of the initial operation. So all of that is just to kind of get us this notion of duality, to be able to talk about disjunctive normal form, because I'm going to leverage that now. But more generally, this concept of duality is a very interesting one, because it lets us just generally think about truth functional operations and how they can be mapped back and forth. So, what can we use this duality for? Well, here's a general idea. Let's say a collection of connectives, truth functional connectives, are jointly expressively adequate if and only if, for any possible truth function, there's a scheme containing only those connectives that captures the truth function. So again, the idea here is whatever truth function you want to have, a TFL language or some connectives are going to be perfectly expressively adequate, jointly expressively adequate, if they can capture that truth function. Fun things, we've been doing TFL with 5 connectives. It's pretty obvious that the biconditional is redundant, right? It's just the conjunction of the conditional going both directions. It turns out that a bunch of the connectives are redundant. Interestingly, we can get TFL expressively adequate systems using just negation and disjunction, using just negation and conjunction, or using just negation and the conditional. It should be pretty clear about why these two are going to work. We'll talk about it in a second. But put really quickly, the reason that we're always going to be able to do these two is disjunctive and conjunctive normal form. I can take any sentence, I can re-express it in, say, disjunctive normal form. I could then replace every occurrence of conjunction with the relevant dual using just negation and disjunction. And so cool, I've now captured every TFL sentence using just negation and disjunction. And I can do the same damn thing the other way using conjunctive normal form. The fun one, and we'll not talk about it, but see if you can figure it out, as to why it is we'd be able to do this. I mean, just to spoil it, we'll talk maybe about it, right? Is the conditional is actually equivalent to a certain kind of structure using negation and disjunction. So if we have that understanding, you can also understand it using conjunction, right? If you have that understanding, then you basically turn sentences into, say, disjunctive normal form. You then replace all of the disjunctions and negations with conditionals and negations. So wham bam. But here's a sort of sketch of a proof for this, right? Take some arbitrary n-place connective. We'll just use circle star, right? By the disjunctive normal form theorem, that is, for every TFL sentence, you can turn it into DNF, right? It's possible to generate a scheme using these connectives, tautologically equivalent to circle star's characteristic truth table. So let's just talk through the first one, right? You take some sentence, you use the DNF to produce the relevant version using only negation, conjunction, disjunction. Since conjunction and disjunction are duals, you rewrite the scheme, just replacing all of the cases of conjunction with the relevant negation, disjunction, dual. Cool. Now all you've got is negations and disjunctions. You have something that's guaranteed by definition to be truth functionally equivalent. You now have reduced everything just down to those two. Conjunction, same damn thing. Disjunction, again, you can map these as you like. Whenever you have the disjunction, you can turn it into this conditional. Whenever you have the conjunction, you can turn it into that conditional. You then get a mapping from every truth functional operation back down to just these two. So that's kind of neat, right? We could get away with just two. Could we get away with just one? Could we have done everything in TFL with only one truth functional connective? Because again, it was obvious when I introduced you to the 5 connectives for our language, for TFL, biconditional is redundant. Given what we're saying here, at least one of conjunction and disjunction is redundant, and then by stipulation, the conditional is also redundant. So there's 3 different pairs we could get away with. Could we get away with just one connective? Weirdly, there's two-place connectives that we could have used to characterize everything we want to do in TFL. So let me introduce you to 2 new connectives. You might have come across these depending on the kind of programming you've done already. So first we have the Sheffer stroke. It's also sometimes expressed as NAND, that is not and. And then Peirce's arrow, or very unhelpfully sometimes called amp heck. I am never going to fucking call it that because no one ever calls it that, right? But we can just, to symbolize them, we can use the upwards arrow for the Sheffer stroke and the downwards arrow for Peirce's arrow. The neat thing here is that these 2-place connectives give us a way to capture the 1-place connective that is negation. So we can say that negation A is tautologically identical to A NAND A. And similarly, negation A is going to be tautologically equivalent to A arrow A. Because that's going to be the trick. Note that all of the previous ones where we were talking about pairs, we had negation and disjunction, negation and conjunction, negation and the conditional. We always had to have negation. Why did we always have to have negation? Because weirdly, negation is the one connective where the top row of our truth table, our characteristic truth table, is false. All of the other ones, if you feed in truths, it outputs truth. So one of the things we would have to have if we're going to have a single operator that captures everything in TFL is the top row, when you input truths, has to output falsehoods. The other issue that we'll have to have is that it's going to be at least 2-place. Because if whatever operator we're fundamentally going to use, it's got to capture conjunction, disjunction, the conditional, the biconditional, all of which are 2-place connectives. So we always were going to have to pull some kind of trick like this. And note, we have these basic structures here. So A disjunction B is going to be tautologically equivalent to this hideous mess using only the Sheffer stroke. And A conjunction B is going to be identical to this mess using only the arrow. So I want to show you how it is that we can get everything in TFL from these, but to get there I want to quickly argue, it's going to be very quick, argue why we couldn't do it with any of the other 2-place truth functional connectives. And to do that, what we can do is just think about all of the possible options. So let's think about all of the characteristic truth tables we might construct for 2-place truth functional connectives. We already know 4 of them. We know the one for conjunction, we know the one for disjunction, we know the one for the conditional, and we know the one for the biconditional. Here are a few more. So I'll just introduce these using our circle star again as just a label. Circle star with a number. So here's just 4 that we can also add to the 4 we know. None of these are going to be adequate by themselves. None of them are going to be adequate by themselves for the reason I said a second ago. None of them can capture negation, because every one of them gives us true when we input truths. And to capture negation, we have to have the case where we input only truths and get out a falsehood. So the 4 that we know already, and these 4 other ones can't do the job. They just can't. Now before I go on, does everybody kind of see why? Again, the thought is we're trying to get back every possible truth functional connective. Negation's one of them. Negation is one where the top row is false. So these, no matter how we string them together, is never going to give us that. So here's the other kind of fun one. Let's take the ones where, cool, the top layer gives us falsehoods, but the bottom one also gives us falsehoods. So in these 4, again, they're not really ones that we've encountered, but they're ones we could define, 2 place connectives we could define. The top row gives us that part of negation. Feed in truths, it outputs falsities. Problem, the bottom row here also gives us falsities. Feed in only false, it outputs only false. And this is equally bad because it's not capturing negation either. Because not only is it such that for negation we feed in truth and it gives us false, but we also have to have you feed in false, it gives us true. Because negation's a flipper. So the top row of the negation table is true to false, the bottom one is false to true. So if we're going to capture negation with a 2-place connective, we need to have the top row say false and the bottom row say true. So let's think about what's left, right? Let's think about what's left. We have the 8 that we've defined. Right, to go back a slide, there's these 4, which couldn't do the top row. There's these 4, which couldn't do the bottom row. There's the 4 we already know, which can't do the top row. We don't have much left, right? We've only got 4 options left. So interesting, you might think of these 2. These 2 are half of the ones remaining. These ones have what we might call redundant positions, where the truth value of the output is entirely determined by the truth value of one of the inputs. So for example, right, the top row, they're both false. The bottom row, they're both true. Cool, so we're getting negation. But here, for our number 9 connective, it's entirely determined by what happens with B in both spots. And for number 10, it's entirely determined by what happens with A. Now, importantly, if we think about these, there's lots and lots of the connectives that these could not capture on their own, no matter how we structure them. Just to give you an example, they can't get this one. They can't get the one where it's false no matter what. Because when you start to feed stuff in, well, it's going to be true or false depending on which one of the ones we're focusing on. So it can't give you the always false operation. There's no way to iterate it in the right kind of way. Similarly, if you remember, number 1 is the all true operation. No matter what you feed in, it spits out truth. Not a very helpful connective, but it's still a connective you could have. And neither of these will capture that because it depends on which input you're giving that will determine whether it's true or false. So these ones can't do the job either, even though they tick the boxes with regards to the top and the bottom. So what's left? Well, we've eliminated 14 of the 16. All that's left are the 2 with the Sheffer stroke and Peirce's arrow. These are the only two left, and conveniently, they do the jobs that we need. The top row for both of them gives us false, just like negation. The bottom row gives us true, just like negation. And the middle ones here are determined not by just one input. Note how, right, it flips between, it's not focused just on the A input, and it's not focused just on the B input. It's determined by the combination of the two. Now, because of that kind of magic, right, it lines up perfectly with negation, and it's not determined entirely by one input, we can now structure these in various ways to give us back every single possible truth function. And again, we have these that we'll be able to use. So let me give you the proof. Again, it's more of a proof sketch, but it's still worth seeing. To show that, right, the Sheffer stroke is expressively adequate by itself, here's the process. Take any TFL sentence. Use the disjunctive normal form theorem to produce some scheme featuring only negation, conjunction, and disjunction. Right. Since we know that conjunction and disjunction are duals, replace every conjunction with the associated structure. Cool. So now we've just got negation and disjunction. Now to go back a slide, at that point, we can use these two equivalences to generate sentences just with the Sheffer stroke. Not the most beautiful thing in the world. It's going to have a hell of a lot of up arrows, right? But it's guaranteed to capture whatever you started with. We take whatever structure you have, produce it in DNF, replace all the conjunctions with disjunction, use these to replace all the negations and disjunctions with a hell of a lot of upwards facing arrows. So cool, right? At that point, we know that anything we wanted to express with TFL, we could express just using the up arrow. It can capture any truth functional sentence we want. It's jointly expressively adequate on its own. The argument for Peirce's arrow doing it is going to look very similar. Right? We use the DNF theorem to give us sentence just using negation, conjunction, disjunction. We replace every disjunction with the associated structure featuring just negations and conjunctions. That gives us just negations and conjunctions. To go back 2 slides, we then use these two equivalences to replace all the negations and all the conjunctions with the associated just crap load of downward arrows. So the neat thing is, we could have done everything we've done using just either this function or this function. So fun question, why didn't we? Why didn't we just do everything using NAND? If you want to see why, just try and convert a very simple TFL sentence into one that features only, say, this operator. Just to take the one that I started with like A conjunction B biconditional C. Cool. That's going to have, I think that one has about 10 different NAND arrows in it. And have fun remembering where they go. Put another way, we don't teach you TFL using these connectives because it's just fucking impossible for humans to perform these actions. We will screw it up, inevitably. So we use redundancies. We use the kind of 5 connective system because it's easier for us to process. But when you actually think about programming these sorts of moves into, say, a computer, not a meat computer, but one of these, the really, really nice thing is that because it's guaranteed to pursue the operations perfectly, this is a very good way to go. And you get something that's cognitively quite simple. It only needs to know one function. It just needs to know how to carefully layer the function to make sure that inputs always track. So that's kind of cool. This is why a lot of times in programming, you will see like just getting away with something like NAND or something like XOR, right? The exclusive OR, which we didn't even really talk about, but fun thing, see if you can figure out which one of the connectives I defined tracks that. But that's really just the kind of fun stuff with expressive adequacy. It's really getting at the heart of what we're trying to do when we think about things like TFL. I presented it to you in a way where it's as if we're trying to track real world or natural kinds of thought processes and rationality. But that's being really generous. Really, these are just formal systems that we've devised. They're tools. They're tools we've made for specific reasons. And yeah, in this case, truth functional logic is a very, very well-designed tool. But we could have designed it differently, and it would work for different ways. So what I want to wrap up with, and yeah, it's going to take me maybe 20 more minutes, is talking about this idea of what we'll call non-classical logics. So for the duration of the class, we've operated with three basic assumptions. If you remember, I think we talked about these in, I can't remember if it's lecture 2 or lecture 1, but pretty close to lecture 1. So the first assumption we had to do with the fact that there's no gaps. For every sentence, the sentence is either true or it's false. You can call this the law of excluded middle. For all A, either A or not A is true. So there's no truth value gaps. Similarly, we also had an assumption that there's no truth value gluts. That is, for every sentence A, it's not the case that it's both true and false. Or that it's not the case that the sentence is true and its negation is true. You can call this the law of non-contradiction. And finally, we've made an assumption that there were only two truth values, true and false. There's nothing in between. This is essential to TND. Right? Tertium non datur doesn't work if there is a third way. In fact, not just bivalence, but we also need no gaps. Because if we allow gaps, there's a third way. It's gapping. It's neither true nor false. This trio serves as the foundation for classical logic. And in fact, what we've talked about this whole semester has been classical logic. TFL and FOL are both variants of this broad family, all characterized by these three assumptions. Now, the neat thing is, as I was trying to say just a second ago, logical systems are tools. So we have other tools that deny some or all of these assumptions. And these are non-classical logics. Non-classical logics are going to get rid of some of these systems, some of these assumptions, and they're going to give us radically different semantical approaches or radically different kinds of proof systems. The first kind of family we can think of non-classical logic systems are ones that deny no gaps. So again, to go back a slide, that's the idea that for every sentence, it's either it or its negation are true. There's several ways to deny this idea of no gaps. One way, and probably the most fruitful, and also a very Dutch way, is intuitionistic logic. So this was actually developed very broadly by a Dutch mathematician, Brouwer. Brouwer was very interested in constructivist theories of mathematics, so where things would only be true if you have a proof for them. And if you think about truth as having a proof for, negation becomes very hard to understand. Because you can have negation as is false, i.e., you have a proof against the claim, or you can understand negation as I don't have a proof for it. And if you understand negation as we lack a proof for it, you're very quickly going to get truth value gaps. I don't have a proof for A. I also don't have a proof for not A. That is, that A is false. I have a proof for neither. In that case, you actually get some very, very weird things, right? It's not the case that A or not A. Why? Because I just don't have a proof for either one. Similarly, double negation turns out to be very strange. If we read negation as I don't have a proof for, double negation is saying I don't have a proof that I don't have a proof for A. And that's not the same as not having a proof. Because you might have one and just not recognize it as such. So double negation elimination fails in these cases. You get a whole slew of things. Intuitionistic logic also rejects explosion because that relies on effectively collapsing a single and double negation together. You have to deny some De Morgan laws, specifically the ones that move negations out to the front. And you have to basically re-understand how negation works. And this leads to a whole slew of variations with regards to our truth tables. So the truth tables can't work like they did before. Another version, another kind of non-classical logic that denies this principle of no gaps is relevance logic. Relevance logic is motivated by the idea that the conditional is too weird. So if you remember, when we were first introducing the conditional, I said things like, hey, here's a true conditional. If there's exactly 50 people in this room, then there's exactly 5,000 people in this room. That doesn't seem right, says the relevance logician. So what they try to do is to block these paradoxes of material implication by modifying the conditional. In particular, the conditional is true if and only if the traditional definition, right? It's not the case that the antecedent's true and the consequence false, but also there's a connection between the antecedent and the consequent. So this is the real trick with relevance logic, is defining how we can say that the parts are about the same topic in some way. Because they still want to block the kind of case I just gave, where there's exactly 50 people, then there's exactly 5,000, though there's a sense in which those share a topic, because it's about the people in the room. So this is a big trick for this system. But the neat thing is that, again, they see the conditional's true if and only if. They don't have to say that the conditional's false when it doesn't have the connection. Instead, they will say it's neither true nor false. It's a kind of misfire. So you end up then with a bunch of gaps with regards to the truth or falsity of certain conditionals. Which, of course, given the stuff we said about duality, means that there's also going to be problems with certain issues about disjunction and conjunction and negations distributed appropriately. So there's some fun to be had with rejecting no gaps. You can also have logics that reject no gluts. That is, logics that accept that for some sentences, it and its negation are both true. These are paraconsistent logics. The important thing about paraconsistent logics, strictly, is that they deny explosion. So they deny that from a contradiction, everything follows. The idea here is that they just want to make sure that they don't collapse into triviality. And you have versions of paraconsistent logic that are just basically like TFL, but then they just say, hey, explosion doesn't work. Everything else goes. Interesting system. The more exciting ones are dialethic logics. These are ones that, hey, we're going to deny explosion, but we also think that there are true contradictions. So these are kinds of logics that we often use for mapping people's belief systems, because frankly, most of us end up believing contradictions one way or the other, but we don't think that you believe everything. So you have to find some way to kind of weaken the notion of entailment. It's very, very fun to play around with these. It's very, very hard to motivate them. They're often motivated negatively. And there's a bunch of work here, particularly by Graham Priest, on developing versions of these dialethic logics. They're fun. The last kind of assumption you can reject is, again, this notion of bivalence, that there's only two truth values. And here you just have a family of what's often called many-valued logics, shockingly. Many-valued logics allow for more or less truth values. Probably the most famous one is the Kasewitz's three-valued logic, where you have truth, false, and neither. This actually works pretty easy. It's pretty simple to map this back to our truth tables. But of course, we're going to have to change the truth tables for cases of when the inputs are T or F or N. And it's worth just having a go on your own, thinking about how we would treat these. So some of them are going to be very simple. Conjunction's still going to behave exactly like it does. It's going to fail whenever the inputs aren't both true. But what about disjunction? Right? Disjunctions are cheap. So it seems like you could have something that's true and then disjoin something that's true or neither or false. So the disjunction quickly expands. Negation turns out to be weird, because what happens if you apply a negation to something that's neither true nor false? Again, fun things. Another variation on this many-valued one is fuzzy logic. Fuzzy logic basically allows for every number between 0 and 1 to have some degree of truth. So there's effectively an infinite number of truth values in between 0 and 1. This is a fun little toy. You can map this, or you could use this to relate kind of probabilistic reasoning back to deductive logic. Again, this plays hell with any of your truth functional connectives. It's something fun to do. But of course, you don't have to just give up on one of these assumptions at a time. You might give up on more. And for example, one of the fun kind of applications that we didn't talk about, but is fun to think about, is how to extend modal logic into FOL. So we only talked about it with regards to TFL. If we try to extend modal logic to FOL, the big question is how to make sense of domains. Do we want to have one domain that applies to every possible world? Or do we want to have variable domains? So that is, there's a domain for this world, there's a domain for this world, there's a domain for this world, and they can have different things. Fixed domains make your world, make the whole logic very simple, but they kind of don't make sense, because if what you want to capture is the idea of different situations, one of the easy ways things could be different is this object exists and that one doesn't. What would the world be like if I wasn't here and someone else was teaching? Something like this, right? So these are kind of cases that seem to push for variable domains. But if you have a variable domain, you very quickly get cases of how do I make sense of a sentence in a world where the object that it's about just simply doesn't exist? I don't have a sister, but we can talk about, is it possible for my sister to be 2 meters tall? That's at least meaningful. Whether it's true or false is another question. So to make sense of this modal logic for FOL, we're going to probably have to give up on at least this no gaps thing, maybe also no gluts, maybe also bivalence. Other ones that have to give up on multiple things, these are very near and dear to my heart, are questions about truth and fiction and questions about free logic. So truth and fiction is a very fun kind of concept where what we try and understand is, what does it mean to say things like Deckard is a replicant? Well, obviously he isn't, because he doesn't exist and there are no such things as replicants, at least not yet. So we can then reread it as it's true in the fiction that. So we introduce this kind of weird operator where we have a place for the name of the fiction, we have a place for a sentence, and this is something like an according to operator. And the fun thing is that truth in fiction is going to have to allow for gaps, because there's plenty of times where fictions just simply don't settle a matter, right? Does Holmes have an even or odd number of hairs on his head? There's no answer. So there's gaps. There's also seemingly impossible fictions. These are fictions that include contradictions as their content. The Holmes stories are a famous example because there was a mistake. So, in some of the early stories, they ascribe Watson's wound on his leg. In some of the later stories, they ascribe his war wound on his shoulder. So it seems like he's got a war wound in different places. Cool. So contradiction very quickly. So you get fictional inconsistency, and how do we make sense of this? So truth and fiction kind of discussions bring together all of those different problems. And finally, you have this sort of free logic stuff, which is very close to the variable domain talk. This is how do we make sense of claims that feature objects that don't exist. So, right, I don't want to ruin anybody's Christmas, but Santa doesn't exist. I know, it's a tragedy. But he's telling you he doesn't exist, so it's fine. But of course, if Santa doesn't exist, how do we make sense of, like, Santa Claus wears a red suit? Not just in terms of whether it's true or false, but how is this even meaningful? Because the thing that we're predicating, or the name that we're using, is empty. So we can't even parse this sentence. It would be basically like saying, wears a red suit. There's no sentence there. There's a kind of gap, a failure. Even worse, we have claims that are negative existentials. Santa Claus doesn't exist. It looks like for this to be true, this needs to name something. But of course, if it names something, then the non-existence claim is false. So we have to find some weird way to make sense of these kinds of negative existentials while allowing for the term to be empty. And there's a couple ways to go. You can be a negative free logician, which is that anytime you use an empty name, the claim is false. That's very bad for these ones. You can be a positive free logician, where anytime you use the empty name, the claim is true. That's very bad for ones like this. You can be a neutralist, where it can be true or it can be false, which gives you the right answers here, but doesn't explain why. So you're screwed no matter which way. But it's a fun little project to think about. Anyway, again, this is basically me just sort of showing you my Pokemon. Right? Like, hey, there's this fun stuff. Come think about it. But, okay. That's really what I wanted to go through. I wanted to introduce to you this general idea of duality. I wanted to then use it to talk about this concept of expressive adequacy and give you the quick and dirty arguments for only the Sheffer stroke and only Peirce's arrow as the truth functional expressively adequate connectives. And then finally present to you very briefly this sort of smorgasbord that is non-classical logics, all driven by giving up on this no gaps, no gluts bivalence assumptions. None of this is going to be exam stuff. It's just kind of, this is fun. I hope it's interesting. So, where do we go next? Well, I think the thing to do first is to very quickly say, hey, really nice job, guys. Right? In the last 13 weeks, we've covered the syntax and semantics for 2 formal languages. We went through some very basic set theory just to kind of wash our mouths after the midterm. We went through the syntax and semantics for modal logic, and then we went through the proof stuff, right? So we went through natural deduction for both TFL, and we're working through FOL. We're going to keep practicing on FOL as we go forward. But before we do that, you should be proud of yourselves, right? This stuff can be very difficult, and we're doing very well. And we've covered a lot. We've covered quite a bit of stuff in these 13 weeks. So, good job. Importantly, the last lecture, just like the one right before the midterm, is going to be nothing but review. Won't be any content other than just kind of briefly presenting to you the structure of the final exam, reminder about how your grades are done, and then any questions people have. So come along if you want, if you have some questions, no worries if not. Note that this week for tutorial, we're going to go through some more natural deduction proofs for FOL. So these ones are going to be ones that focus on using identity, but it will also rely on the stuff we talked about already. And then finally, for the tutorials that we'll have next week, what we're going to do is we'll go through a practice final exam. It will have the exact, just like with the midterm, the practice final will have the exact same structure as the real midterm, or sorry, the real final exam, all of that stuff. I'll also mention some stuff about the timing for resits and things like that. But cool. Thanks for coming, guys. Good luck with the rest of your day, and I will hopefully see you later in tutorials this week.